Thanks for having me. So the way that we have structured this talk is I'm going to try to set the stage a little bit, and then both of the things that we're presenting today are very much different rabbit holes that Elijah and I went down when we started thinking about silicate clouds in exoplanet and brown dwarf atmospheres. So first of all, hopefully this is preaching to the choir, but just to get everyone on the same page, the power of both clouds and hazes in planetary and brown dwarf atmospheres is that they're really tracing out temperature processes for us. So I really love this cartoon from Peter Gao, where it's showing at the very hottest of atmospheres that we measure, we might expect something like aluminum oxide clouds to be the dominant cloud that we see observationally. And then as we go to cooler and cooler temperatures, there's this whole swath of phase space where silicate clouds should be dominating the cloud layers that are apparent to us. At some point, we probably get cool enough that hazes or maybe salt clouds start appearing, but I'm going to totally ignore those for this talk. And this is not just true in exoplanets, it's also a sort of defining feature of how we set the brown dwarf sequence. And so you can see here that in color magnitude space, as we move from M dwarfs to L dwarfs, we see this really strong reddening that happens. And that's thought to be because we're seeing the presence of these silicate clouds start to redden these particular filters really strongly. Eventually, you get cool enough that although those silicate clouds are still there, they're deeper in the atmosphere. And so you start to see much bluer colors again, and those end up being the T dwarfs. And eventually you get cooler again and start actually pulling out alkali and maybe even water clouds that redden you again. So this is very important observationally. So much so that even the very first measurement we made of a transiting exoplanet, here is shown HD 209458b in the middle there, we saw the presence of clouds. And so you can see that in the sodium feature. This doublet is much weaker in the data than the model would predict. And that was inferred to be because there's this extra opacity from the clouds. This is also true of brown dwarf observations, where again, we're seeing smaller than we would have otherwise expected absorption features because of this additional cloud opacity. And even before we had those observations, we were pretty sure, based on just simple thermodynamics, that these were some sort of silicate. And so on the left here, I'm showing you some temperature pressure profiles of some brown dwarfs in these dotted lines, in this A and B. And then the solid lines are showing the condensation points or lines of various kinds of species. And so you can see that MgSiO3 line is directly crossing over this A pressure temperature profile at pressures where we are probing observationally. With Spitzer, then, we were actually able to measure and confirm that these are in fact silicate clouds. And so you see this deep absorption feature in the like 8 to 10 micron region, which is exactly where you would expect this SiO bond to be. You could actually do one better and think not just about the chemical species and how that's controlled by temperature in these atmospheres, but also the morphology of those cloud particles you're seeing. And the difference here is basically amorphous on the top, and that's something glassy where you've condensed your cloud particle and then immediately cooled it far below the crystallization temperature. And so then you get these nice smooth absorption features. On the bottom is a crystalline structure for these particles where you're keeping them hot long enough, or maybe they've cooled and then are getting hot again. And so then they start to crystallize. And when you see that, you get this much finer structure that makes up your absorption feature. And so that's already telling you something about the process of how these clouds got made. And so been known for a long time in brown dwarfs, but then there's also evidence from hot Jupiters that these clouds are important to, not just theoretically, but observationally. And so this paper is showing the strength of the water feature as measured by Hubble's with C3 as a function of temperature. And so you see this peak and then drop off exactly where you'd expect silicates to start condensing and shrinking the water feature that we're able to measure. And so Peter Gao and collaborators ran a whole bunch of different microphysical models that show at these temperatures, you would expect these magnesium silicate clouds to really be dominating the cloud mass at these temperatures. And so, of course, it would be nice to have then immediately gone and measured that with Spitzer, but by then we didn't have Spitzer's cryogenic capabilities anymore, and so we had to wait for JWST. And so now I'm showing this plot from Hannah Wakeford showing that all of these interesting silicates absorb exactly where we can measure with JWST's MIRI instrument, and they should be really strong features. And so they should be, in a sense, low-hanging fruit for us to go chase and see if this picture of how clouds work in these atmospheres holds together. But right before we had JWST, I've kind of harped on magnesium silicates for a minute to set the stage here, and that the picture might be more complicated. And so this is an L-dwarf observation from Ben Birmingham et al. And to fit the cloud feature here, he threw like every model he could think of, I guess, at this data set and determined that it actually probably has a significant contribution of SiO2, which is not predicted to be stable in thermodynamic equilibrium at the conditions that were originally being modeled. That's interesting. And in keeping with a lot of brown dwarf observations, it seemed to be better fit by an amorphous structure versus crystalline, which for me as a theorist and experimentalist is really annoying because at the temperatures we should be probing, I would expect them to be crystalline. So how you explain seeing something amorphous is nagging. And of course, I'm sure that you all have seen this before, which was like the most exciting paper to me that came out in 2023, where on WASP 17, you get this beautiful, just really striking SiO2 feature in its transmission spectrum as measured by MIRI. And so again, we're seeing SiO2, or maybe we would have previously expected magnesium silicate. And so this is just kind of demonstrating again that this feature fits really well, but that maybe not perfectly, which is kind of a thought for later, that the peak of this exact absorption is a little bit offset from this SiO2 absorption that Grant et al., including Elijah, were able to model. And then you can get at things like the particle size distribution that best matches this feature. And then you can also do this same exercise of, is it amorphous or is it crystalline? And in this case, it seems to be crystalline, which makes me happy because that's what I want it to be. But again, it doesn't quite perfectly fit. And so this whole thing of determining, okay, we don't just see magnesium silicates, we also seem to see SiO2, and there are ways you can do that, not invoking thermodynamic equilibrium. And so Christiane Helling and collaborators have been making lots of SiO2 for a long time by considering a dirty grain approach where it's non-equilibrium chemistry forming these clouds. And so maybe that's being pointed to of what we're seeing by seeing SiO2 and not magnesium silicate. But then even more recently, this paper came out led by Emily Calamari showing you absolutely can make SiO2 in thermodynamic equilibrium, and it just depends on the balance of magnesium to silicon you have in your atmosphere, and that determines how you sequester those clouds into different species. So we're starting to put together this understanding of, based on the chemistry of how this is working, but we can actually do one better. And so when I got really excited about this WASP 17 result, I started talking to the people in my department at the time at the University of Arizona. And I ended up talking to a geologist, and he looked at me and he was like, well, why do they keep calling it quartz? It makes it no sense for it to be quartz. And that's because there are other polymorphs of SiO2 at these high temperatures and low pressures. And so on the left there, I'm just showing you all the different crystalline structures, all the different polymorphs you can make out of SiO2. And they're stable under this phase diagram, which annoyingly, hopefully for all of you, as it is to me, is shown in kilobar, which is a unit that I don't really understand, and in Celsius, which is a unit I halfway understand. But the whole way that this plot is displayed, I care about this tiny little sliver at the bottom. You can see there that tridymite and cristobalite are the things that are actually probably active or stable at the temperatures that we're probing. Because if we think about, again, going back to this brown dwarf sequence, we're probing things less than a bar in above 1,000 Kelvin. And so that should absolutely be not quartz, but one of these other crystalline forms. And so I decided to remake that pressure temperature phase diagram in units that I understand. And so I'm showing you here in the different shadings, the different kinds of polymorphs, and that will correspond to where I've plotted them on the left. So now we've put temperature in Kelvin, and we've put pressure back in bar, and we're looking at things at millibar pressures, which is where I'm much more comfortable. And then I've overplotted here in the solid lines, different temperature pressure profiles of where we have detected SiO2 clouds. And then these dotted lines are corresponding to the condensation curves at various metallicities. And so where they cross, you can imagine that that's where your clouds are initially forming. And for almost all of these cases, we see that they're crystallizing for WASP-17 at the cristobalite point, and for this L dwarf in the tridymite stability region. So that's great. You can go ahead and say, sure, these are in fact these different kinds of polymorphs. But the power here is that these different crystal structures necessarily have different bonding lengths and arrangements, which is exactly what we're measuring spectroscopically. So then I wanted to ask the question, are these different things observable with the observations that we have? And so to test that theory, I used these two different open source modeling tools, the Virga Cloud Code and Picasso. And just because it's coming out like probably this week, I want to plug that Picasso version 4.0 is accepted. You can already grab it from GitHub. And I think the accompanying paper led by James Meng will be out very, very soon. That is a total aside. And so the first thing you would want to do when you are running these kinds of models is actually get the optical properties of these different materials. And so I was able to compile data, and there are stars there because I'm seeding thought for later. You can see that the different polymorphs of silica are distinct in at least refractive indices space. If you then run a Mi code to figure out what their Mi coefficients, which is actually the thing you're going to feed into the atmospheric model, those are also distinct. And so then I just did exactly the same modeling exercise as was done with the original Picasso models for WASP-17 to see, does that change the peak at all? And then I ran the statistics on the fit. And so at least for cristobalite, you do get a better fit than quartz, although it's not meaningfully better. And that's mostly down to the data quality, but could also be due down to the fidelity of our lab measurements of these materials. Tridymite, you can see, is actually a much worse fit, but I actually don't trust this result at all. And that's because of what I mentioned earlier, that this region that fits really badly here is exactly where I did the most terrible stitching together of lab data that's not compatible, that was missing, that I had to fudge some numbers. And so I do not trust this region at all. And of course, it's exactly where it fits the worst. But what I think I'm demonstrating here, that if you had just a little bit better of data quality, you could in fact differentiate these different kinds of polymorphs. And then I want to go back to this thing that I've been talking about the whole time, is we can use these clouds as tracers of the atmospheric physics. And so here I'm showing different cloud detections that have been made of these silicates, and then the regime where you might expect them. That's highlighted here. And I want to call attention in particular to this planet, WASP 107b, which I have been plotting on my previous phase diagrams, but it is not in the expected silicate cloud regime. It is way too cold. And so we can do a fun thought exercise, because supposedly these clouds are there. You see this strong feature here, where in this discovery paper of the clouds, they attribute them to some sort of mixture of different silicates because of this structure right here. And so now I want you to look specifically at this teal set of lines. And so that's the temperature pressure profile, which you can see go through all the different silica polymorphs. But the actual condensation curve and where it crosses that temperature pressure profile is actually in the melt phase of this material. And so you'd have to imagine that your cloud condenses there and then rises all the way to like up there, where the contribution function from this set of models determines the cloud should be. And so if it's traveling through all of these different stability regions, you could do a fun little what kind of material should it be based on other constraints we have about the atmospheric mixing. And so if you assume some sort of mixing timescale based on the scale height and the mixing to figure out how long it spends in each region, we can assume the scale height is like 800 kilometers. We have an independent measurement of this KZZ value from the fact that we see less methane in this atmosphere than otherwise expected, which both Wellbanks et al. And Singh et al. Have inferred to mean that you have very vigorous mixing from below. And so you get this dynamical mixing timescale of like 3.5 hours, which, just as an aside, means your particle is going vertically straight up at the speed of a Category 4 hurricane, just to kind of give you some sense of how dynamic these atmospheres are. And then to imagine it's going from that like 30 bar to a millibar where we actually see it means that this is taking on the order of 40 hours for this to all happen. If you can break it down even further and figure out it spends like 2 hours in the cristobalite stability region and maybe 7 hours in the tritomite region and the rest in quartz. And that is plenty of time for crystallization to set in. And so maybe we're actually seeing some mixture of these different crystalline types in this one cloud that we observe in a single spectrum. And so I hope I've convinced you that if we had good enough lab data, good enough models, and good enough observations, we can actually tell this story of how these clouds are working to reveal the physics of these atmospheres to us. And because they're specifically minerals, we should expect different crystalline forms for basically any mineral cloud that we might look at. And these, in some cases, are spectrally distinct. So I'm trying to posit that we need to think about cloud condensation, not just in terms of chemistry, but also in mineralogy. And that really we are tracing out the physics using these cloud structures, and they are in some cases observable with JWST. So I'm happy to take any questions based on that.
Great. Thank you very much, Sarah. Do we have any questions right away? Just raise your hand using the feature to let me know you have a question, or alternatively, you can type something in chat. Anna.
Hi, very nice talk. Very interesting. I was just interested because you eventually came around to the point that the stuff might start off as melt. How important do you think it is for the thing that you still observe? Is there even molten material left over when you observe the top of the cloud, or is that all crystalline at the top?
I would think, I mean, it's going to depend on the specific atmosphere you're observing. So if you happen to have a temperature pressure profile of a planet that's really hot, I think it's conceivable you could measure melt. But I think for most of the hot Jupiters, we're either going to measure some sort of crystalline form or possibly an amorphous form if it did condense as melt, but then get flung very quickly to cooler regions of the atmosphere. And so then it would be sort of like a glassy material. I don't think you'd ever, I think it's relatively rare you would ever actually see like a liquid melt cloud particle.
Okay. Thank you. If I may follow up on it, would that change if you had jets going around and changing the climate over time?
Possibly. I'm very interested in this question of like, okay, I've completely talked about vertical mixing. Elijah next is going to talk about other kinds of mixing. And so maybe he has thoughts too. But I don't have answers, but I am very interested in this question of like, okay, not only do you have just up and down of how these clouds are changing with thermal gradients, but they should also be advecting around. And so that also maybe changes the structures that you'll see depending on the temperatures that they experience along the way.
Thank you.
I don't have an answer, but I think that's an interesting question.
Any other questions? I'm also happy for people to ask questions of either Sarah or Elijah at the end if something comes up as a result of both talks. What was it? I was just going to ask actually, why? So you said you don't expect a morph, or you weren't expecting the amorphous species in the case of the brown dwarf. Why is that? Is that based on the vertical mixing of brown dwarfs in particular, or something else?
So generally, the temperatures that we're probing for the brown dwarfs are still above 1,000 Kelvin at the cloud layer that we're seeing, which is above the crystallization point of most of these materials. And so even if it formed as amorphous through some process, I think eventually it should be held at a elevated temperature long enough that it crystallizes. And so you could maybe think about arguments where maybe it's advecting around. I mean, for brown dwarfs, this I think maybe is more possible for hot Jupiters because you have these strong day-night temperature contrasts, where because brown dwarf is internally heated more than anything else, you're not really expecting the same kind of strong day-night contrast. And so I just can't imagine a scenario in which you're ever getting cold enough long enough to see something that's amorphous.
Okay, great. Thank you. And there's also a response from Elijah in the chat.
Oh, it was just about the partial melting. So I have thought about this a little bit where maybe some partial melting is occurring of the aerosols as they advect to the dayside, similar to what happens with micrometeoroids on Earth, where they partially melt and turn perfectly spherical. Definitely interesting to think about how that would change shape and composition of these aerosols, but not too sure how fast they would cool and how all of those things interplay with each other.
Okay, great. Shall we move on? So Elijah, do you want to share your screen? Yeah, and
Can y'all see that?
Yes, it is in a vertical line. It's a weird aspect ratio, and that's something else. Yeah, okay. Yeah, that's
Is that better?
Yeah.
Okay. All
Great.
right.
Thank you. Take it away.
Yep. So thank you for coming to this joint seminar, and thank you for the opportunity to present my work. I'm Elijah from Cornell University, and today I'll be presenting kind of my side of the rabbit hole that I went down with my advisor, Dr. Nicole Lewis, on observing grain directionality in exoplanets. All right. So in 2023, Sarah mentioned this already, but I worked on a project with many of the people that are in the seminar where we found the first ever direct evidence of silicate clouds in the transiting hot Jupiter from the MIRI LRS transmission spectra of WASP-17b. And this was due to excess absorption at that 8.5 micron region, which is shown here. And we attributed this to sub-micron crystalline quartz. A study released pretty soon after, again, found evidence of crystalline quartz on the dayside of the quintessential hot Jupiter HD 189733b, again due to excess absorption at 8.5 microns, which I've just circled here. So by 2024, two hot Jupiter JWST spectra have shown evidence of absorption due to silica, and not just silica, but its crystalline form of quartz or potentially some other polymorph, but the important part here is crystalline. So Sarah touched briefly on the difference between the two material forms, amorphous and crystalline, but I kind of want to go over it again really quickly. So amorphous particles, also kind of known as these glassy solids, form due to that rapid cooling, where they cool so fast that the internal structure inside of them doesn't have time to form a crystal lattice. So the bonds are frozen in place and randomly oriented. Crystalline solids, on the other hand, have a highly ordered internal structure and a crystal lattice. And silicates can form into crystalline two pathways. They either nucleate directly into the crystalline form from silicate gas, the implication here being that they cool slowly enough that the crystalline lattice can actually form, or condensed amorphous solids can anneal into a crystalline form. So if they experience hotter temperatures than they formed at, the crystalline lattice will form inside them. And this timescale is about a few hours at 1200 Kelvin. So the expected form of silica in hot Jupiter atmospheres, either through direct condensation or annealing, is crystalline. And due to the difference in their internal structures, a crucial difference between amorphous and crystalline solids is that they interact with light differently. So before diving into how this property propagates to exoplanet observations, I want to take a moment to show some examples of how crystalline ice interacts with light on Earth. In particular, crystalline ice particles suspended in our atmosphere interact with light in a way that produces a myriad of beautiful optical phenomena that I've shown here. These phenomena are not only really neat and pretty, but they also provide an insight into the local atmospheric processes that the ice crystals are or are not experiencing. And I wanted to go through a few of them in particular. The first is the titular sundog. So sundogs form due to hexagonal ice crystals being horizontally oriented towards us on Earth. And these form because as the ice crystals kind of fall through the atmosphere, they just naturally align so that the flat face is going down. And this is kind of has an indication that the atmosphere is calm enough that no wind is flipping these ice particles around. They're just allowed to kind of settle and form this horizontal alignment. And as the sunlight goes through the ice crystal, it refracts towards us and forms these prismatic mini rainbows on the left and right hand side of the sun. And I have a few pictures here that I've taken and my undergrad took on the right. A very similar process forms these phenomena called sun pillars, where again the ice crystals are horizontally aligned, but instead of refracting light, the light is being reflected down to the observer. And again, this kind of just means that the ice crystals are allowed to settle and fall through an atmosphere without any wind or turbulence messing up the alignment. On the flip side, we have these moon and sun halos. So if you ever gone outside at night and seen kind of this ring around the moon, that's a moon halo. And this is caused by randomly aligned hexagonal crystals. So this can mean maybe there's some turbulence in the atmosphere that is causing the ice crystals to not orient horizontally as they fall through the atmosphere, or the ice crystals are just so small that they're not aligned with any process in the atmosphere. These phenomena not only probe purely dynamic processes like turbulence, but can also probe things like electricity. So here's a video of what a phenomena called a crown flash, where the ice crystals above a storm cloud align with the electric field above the storm cloud. So you can kind of see this pillar of light / rainbow thing kind of flip back and forth along the electric field of the storm cloud. And finally, these processes are not just unique to Earth, nor unique to water ice crystals. A sun halo has been observed on Mars from the Mars Perseverance rover seen here on the left, and it's also been predicted that octahedral ammonia crystals on Jupiter and Saturn can form these refraction halos with up to 4 sundogs, and that's just due to a difference in the shape of the ice crystal there. So I hope I've convinced you that the unique ways crystals interact with light provide a way to probe which atmospheric processes the particles are experiencing. However, all the phenomena I've shown in the last few slides are solely due to the refracting and reflecting of visible light, which is not something that is accessible to probe remotely on transiting exoplanets with JWST. So the next thing to explore is whether or not we can probe these same anisotropic effects in the mid-infrared, and if so, what can we learn? So moving back to mid-infrared wavelengths, silicate aerosols have these diagnostic absorption features in the 8 to 12 micron range that allows us to detect them in JWST data. In the beginning, I claimed that we found stronger evidence for crystalline aerosols over amorphous ones, and that's due to crystalline aerosols having a more fine structure to their absorption feature than their amorphous counterparts. So here in orange and pink are the cross sections of crystalline quartz and forsterite respectively. And then their amorphous counterparts are seen in the back in turquoise and purple. However, how crystalline materials absorb in the mid-infrared goes beyond just the structure of their absorption feature, but also their orientation relative to incident radiation. This is true in visible light, but also in the mid-infrared. So in order to understand how different crystals interact with light, we do have to dive a little bit into geology, so just bear with me a bit. First here is on the left, I have spinel, which has a cubic crystal shape. And cubic crystals are isotropic, meaning that the way they interact with light doesn't depend on their orientation relative to the incident radiation. On the flip side, we have quartz and forsterite, which have a trigonal and orthorhombic crystal shape, which means they do interact with light anisotropically. Specifically, quartz is uniaxial and forsterite is biaxial, where biaxial crystals have a stronger dependence on their orientation than uniaxial ones. So starting off with quartz, which is a uniaxial crystal, this means that it has two sets of refractive indices that go with it. So we have the ordinary refractive indices, which describe how light interacts, light that is polarized perpendicular to the c-axis, which is this up and down axis, interact with the crystal. And then we have extraordinary refractive indices, which describes how light polarized parallel to the c-axis interacts with the crystal. And if you want to think about the kind of average contribution of the ordinary and extraordinary refractive indices, you can consider this idealized situation where you have light propagating through the side of the crystal, shown here on top, and light propagating through the top of the crystal, shown here in the bottom. And if light's propagating through the side of the crystal, it's going to interact with both the ordinary and extraordinary refractive indices. But if it's propagating through the top of the crystal, it's only going to interact with the ordinary refractive indices. So the ordinary refractive index has about a 2/3 contribution, where the extraordinary has like a 1/3. However, as we'll discuss a little bit more later on, the actual way that you weight these two sets of refractive indices depends on the actual orientation of the crystal. So this plot is showing wavelength versus computed cross-section. And in gray here, we have the sets of refractive indices that have been commonly used by the exoplanet community. And then in green and blue, we have the cross-sections you get if you take the extraordinary and ordinary refractive indices. And if we're just focusing on this 8 to 9 micron region, which has a quartz feature that we use to detect quartz in WASP-17b and HG189, you can tell that if you weigh these extraordinary and ordinary cross-sections in different ways, the way this anisotropy shows up in the resultant cross-section would just be a change in that peak morphology there at 8.5 microns. So here we have forsterite, which is a biaxial crystal, which means it has 3 sets of refractive indices. Again, the way that you combine these sets of refractive indices depends on the orientation of the crystal, but the average contribution of each set is 1/3. Similar to the previous plot, we have the cross-sections of forsterite presented in the literature here in gray, and then we have the 3 sets of refractive indices here in blue, green, and turquoise. And contrary to quartz, which kind of has the anisotropy show up as a modulation of that central absorption feature, forsterite instead has 3 distinct absorption features that correspond to each of those 3 refractive indices. And here I want to emphasize that even if you aren't interested in the application of grain orientation, taking into account anisotropy is still essential when computing cross-sections of crystalline aerosols. So here in the gray, especially these 2 spiky ones, you can tell that previous sets of refractive indices only really took into account 1 or 2 of the 3 peaks that you actually get from forsterite crystals. And I want to take a quick sidebar on deriving these cross-sections. So for this talk and in my paper, I mostly argue that it's better to derive the cross-sections from each set of refractive indices first, and then weighting the cross-sections after the fact. But other papers have opted to instead average the refractive indices first and then compute one cross-section. And here that's displayed as the difference between the solid navy line, which is averaging the cross-sections, versus the dotted line, which is averaging the refractive indices. For the case of quartz, which is shown here in the top panel, it doesn't make too much of a difference in your final cross-section, but I did just want to mention that for the forced-right, it completely changes the resultant cross-section. So I do want to apply some caution here that the way that you actually average these things can cause large deviations in your resultant cross-section. So now let's look at how we expect these silicates to actually be oriented in hot Jupiter atmospheres. So lab work has shown that silicate crystals, when they do grow, preferentially grow into non-spherical spheroid shapes. They usually grow along one of the crystallographic axes, usually the C-axis. And in my work, we looked at this theory that was presented by a Cornell professor, Tommy Gold, in 1952, called the theory of mechanical alignment, where gas movements align dust in the ISM. And the idea here is actually pretty simple. So if you have, you can think of it as like if you have a lot of boats in a random orientation in a river with a really strong current, if you just let those boats sit, they're going to align naturally with that strong current. Or you can think of a lot of manatees in a river following the current. And though this theory has fallen out of the favor for the ISM, they found that the dust in the ISM is actually more aligned to electricity and magnetism. This theory does work pretty well in the relatively higher gas densities and high wind speeds found in hot Jupiters. So similar to how on Earth, where the observed phenomena depends not only on the alignment of the particles, but the observer's position relative to those particles and the incident radiation. The same principle applies to observations of hot Jupiters. So here we just have a hot Jupiter with silicates whipping around in its atmosphere, and we have the two main geometries that we observe exoplanets in, which is thermal emission and transmission. And if the silicates are mechanically aligned, that means that they're going along with the wind, and it's thermal emission, we're measuring light from the planet itself. The light we're actually measuring is being attenuated through the sides of the crystals. On the flip side, if we're measuring transmission, attenuated starlight, as the silicate crystals are going around the limb of the planet, they're going to be oriented parallel to the starlight that we're observing. So the attenuation is happening as the light's traveling through the tops of those crystals. So here we have actual modeled transmission spectra of quartz assuming different orientations. The black line here is just what happens if you compute these spectra by averaging the refractive indices instead of the cross sections. So I won't talk about it too much here. The important ones are the colored lines. So the green and the turquoise are specific orientations of quartz. And then the blue line here is randomly oriented quartz. So on this zoom in here at the 8.5 micron feature, you can tell that the main difference between these different orientations of quartz results in a different peak morphology. If we go down here to the difference plot, so if the particles are mechanically aligned, we would expect to observe the turquoise top orientation, so the turquoise line, where you see that really deep prong in the absorption feature. And if particles are not coupled to the winds, you would expect to see this blue random orientation. And the difference between the two is up to 350 ppm for WASP-17b. So this is hypothetically an observable effect in transmission data sets. Here instead, we have emission spectra of crystalline forsterite. So now the absorption is going down instead of up. And forsterite is pretty unique when it comes to its orientation. So depending on how forsterite's oriented, out of the three peaks, you would only see two of them. So for example, the side orientation has the EC and the EB peaks, but it doesn't have the E8 peak. And that makes it a very strong probe of directionality, especially when compared to quartz. So the favored, if it's mechanically oriented on the day side, we would expect to see this front orientation. And then versus random orientation, you get about a 300 ppm difference here at the EB peak because that just isn't present when the particles are aligned with the front facing view. The final thing we did in this paper was run retrievals on the current datasets of WASP-17b to see if we could probe directionality with current datasets. For these retrievals, we both assumed random orientation, so we had a strict assumption of randomly oriented particles, and for the second one, we actually allowed it to pick the weighting of the refractive indices separately. So here in the top for randomly oriented quartz, we can see that including the anisotropy of quartz does change the peak morphology compared to what we saw in Grant 2023, where you have this double prong feature in the mid-infrared. Otherwise, if you just let it freely pick which set of refractive indices it likes better, it prefers near 100% extraordinary, which does end up being unphysical because it can only have a max of 50%. And that's because the ordinary, which has this double prong feature that the data doesn't like as much. Incidentally, this is also the data we used for Grant 2023 to fit the quartz feature was also 100% extraordinary. So this means that there could be potentially, maybe as Sarah posited, a polymorph we're missing or just some lab data we're missing when modeling this absorption feature. We also ran retrievals on the emission data set. Here on the left, we just forced the cloud with random oriented forced right to show that there's potential for an absorption feature there in the 9 to 12 micron region that would correspond to forced right's 3 peaks. And then when we let it fit the 3 refractive indices separately, it doesn't actually really favor a cloud except in the 2 sigma region. And out of all 3 refractive indices, it prefers the E parallel A the most, which hints at potentially a top front or randomly oriented force right on the day side. But we're limited here, especially by the SNR of the emission data set. But there's some good news here on that front. Me and Sarah are PIs of a JWST Cycle 4 program titled It's Polymorph in Time, where we're revisiting WASP-17b to get 2 additional transits, mostly to probe for a specific polymorph on the limb, but we're also getting 1 additional eclipse of WASP-17b to try and get better SNR in that 8 to 12 micron region to probe for dayside aerosols and potentially oriented forced right. These are coming down the line this summer, and it's going to be a fantastic test bed for the 2 different modeling rabbit holes that me and Sarah went down. Before concluding, I want to give a quick shout out to an open source collection of exoplanet aerosol relevant refractive indices and pre-computed cross sections I've curated that live in the Poseidon documentation. So there's a base aerosol database, but there's also an additional database that has over 150 temperature and directional crystalline aerosol refractive indices. Additionally, there's a forward model tutorial on how to use these temperature dependent and directional dependent aerosol cross sections in forward models. So if you're interested, feel free to look at the tutorial and documentation, or feel free to just reach out to me too. So in summary, I think if you flew a spaceship to WASP-17b, you would see this very prismatic planet where optical phenomena like sundogs depart from being a rare weather phenomenon to being a global one, due to the constant alignment of crystalline silicates to the winds. However, we can't fly spaceships to WASP-17b, but luckily we can still learn whether or not the aerosols are actually coupled to atmospheric winds or maybe something crazy like electricity or magnetism by leveraging changes in their mid-infrared absorption. So I'll just go ahead and leave my takeaways here and take any questions. Thank you for your attention.
Thank you very much. That's great talk. Really brought me back to first year geology labs and looking at things under birefringence and trying to remember how crystals work. Do we have any questions? hang on, I've lost. Katie.
Hi. Yeah, they were both really, really nice talks. I really enjoyed them. I wanted to ask you, Elijah, about the averaging of either the cross sections or the refractive indices. Um, is there a way to test that experimentally or observationally? Is that what you've done already, or?
Yeah, so I did go down this rabbit hole too, and I think it's one of the appendices of my paper, but a
Yeah.
lot of people can't agree on this either. I think if you took like a global average of the lab papers, most people agree that taking an average of the refractive indices is a better way to, not sorry, an
It's
average of the
easier.
cross sections
Hmm.
is a better way to go about it.
Yeah.
Um, because when you're averaging the refractive indices, you're kind of making up a new they can combine in a weird
Mm,
way that maybe doesn't satisfy Kramer's chronic anymore,
yeah.
or um something can go like you're kind of making a new material that might not be physical. So I
Yeah.
think most people agree that averaging the cross sections is the better way to go.
Yeah. It's interesting how different species have like completely different, they react differently to that. Yeah, that was cool. Thank you.
Do we have any more questions? Anna again?
Very nice talk. I'm really not a crystal expert, so I wanted to ask. You're focusing on phosphorite a lot, but there are other like iron-rich or nickel or titanium-rich variants. Would you just not expect them to be at the right temperatures or not as common to make a huge difference there?
Yeah, so in this paper we mostly focused on quartz, force-rate, and instantite, but the database I curated with like over 150 refractive indices does have TiO2 and some of the calcium and aluminum oxides that you would expect to form in the hottest of hot Jupiters, so ultra hot Jupiters. And I do believe that especially TiO2 and its polymorphs do have their uniaxial crystals, so they do have some directional dependence. But others like spinel don't actually have the directional dependent refractive indices. So again, it just depends on which crystals you expect to form, and then you have to go look and see whether that crystal is isotropic or not, and go from there.
Thanks. Thanks for the clarification.
Hannah.
Hey guys. Given that when we're doing transmission spectra, we're not just getting material we're measuring around the kind of equatorial jet, we've got things across the poles as well. What's the kind of dilution factor we might expect from the orientation of those crystals?
Yeah, that's a good question. So I guess you could kind of expect like mechanically oriented near the equator, like where the jet is, and then maybe randomly oriented where they're not really experiencing any particular forcing at the um, uh, other parts of the limb. But another part, I saw a really good talk at OWL about this, where there's another factor here, and especially at the limb, where you're seeing attenuated starlight, and the radiation pressure from the starlight can also affect uh, the crystals in a way where they orient maybe towards or away from the starlight.
And thinking of observationally, what's more important, high precision observations or high wavelength resolution observations to capture these differences?
So for quartz, I would say you want maybe more wavelength precision because it's such a minute difference in the peak morphology. So you're gonna want like really good resolution to even maybe see that double prong that comes out of quartz. For forced right, I would go more for like just higher precision in general because the three features of forced right, two of them are like in the 10 to 12 micron region. So if you ever want to have a hope in resolving those two features, you're going to have higher precision MIRI observations.
And we'll take one more from, I'm afraid I don't know your name.
Hi, sorry, I'm Liam. Yeah, I don't know why it's showing a bunch of numbers. Really nice talks. I have a question. So you mentioned that the optical properties of silicates depend, obviously on directionality, but also for different polymorphs. Um, I was wondering if there are any degeneracies or kind of overlaps between the spectral signatures we see from different polymorphs and from different directionalities. So essentially, what are the challenges when you have a mixture of different polymorphs with a mixture of different directionalities?
Yeah, I guess I can start. And the quick and short answer is that it is 1000% degenerate. So me and Sarah kind of went down like a rabbit hole. Like after we went down these rabbit holes and other rabbit holes, we were like, this is a degenerate mess. How are we ever going to learn anything? We kind of came to the conclusion that uh, you can still really learn a lot just by knowing these different modeling techniques. Like there are ways you can still learn, even if they are degenerate, you're still learning something really important about the silicates when you are using these different modeling techniques to fit the feature. So if it is like a jumble of different polymorphs, maybe that would make you have like this broader feature that maybe you can't see the directionality because it's so jumbled. Or maybe you have this really clear signature directionality. And all of this would still tell you something really interesting about the atmosphere.
The other, like, yes, I worry about this a lot, that we're just going to end up in degeneracy land. But I think you can use your knowledge of the broader context of the atmosphere to, like, you might have a degenerate result, but you can eliminate certain possibilities that technically fit the data because physically it makes less sense than the other option. And so, like, by understanding the temperature structure of the atmosphere really well through other means, by maybe the chemical species you're able to measure, and getting just really broad wavelength coverage so you understand the scattering at shorter wavelengths, and combined with whatever features you see in the mid-infrared, I think is going to be the way to go, is that doing as good a job as you can with the modeling of the degeneracies, but then putting together the full atmospheric context to try to whittle them down.
Yeah, that's really helpful. Thank you.
Okay, so we've got 5 minutes, and Elijah said he wanted to share some lab results. So there's a very quick opportunity now to go through them.
Yeah, I'll just do this really quick sneak peek. Okay, so me and Sarah last summer, with all these wonderful people on this author list, did some lab work at Goddard for new refractive indices, and I just wanted to show them off really quickly. So there's another kind of angle here that both me and Sarah did not talk about, which is temperature. And the reason we didn't really want to talk about it in our main talks is because when we did look at temperature, so looking at hotter and hotter absorption of silica, the absorption feature moves more and more red, which fits the data actually worse. So it goes the wrong way when you're considering how hotter and hotter quartz. But these measurements I'm showing here on the left were derived from a bulk crystal. So over the summer, me and Sarah used a lab at Goddard to take transmittance measurements of quartz, silica, and tridymite, as well as a bunch of natural samples from 300 to 900-ish Kelvin, temperature-dependent measurements. And part of the philosophy here is that the way we're actually taking the measurements is more analogous to what we observe with exoplanet transmission spectroscopy. And here's just an animation showing our preliminary results of the transmittance of quartz. So we see as we heat it up, there's very large changes in the morphology of the feature. Mostly we recover the fact that it does go red and kind of creates this broader absorption feature. But slightly, something I think is really interesting here too is that we took heating and cooling measurements. And we found that as we heated up our samples, the shift in the absorption feature is near instantaneous within the lab timescales, which are a lot shorter than the timescales experienced in hot Jupiter atmospheres. And when we cooled back down the sample, the same peak morphology was recovered. So this means that aerosol absorption in particular is a really strong probe of in situ temperature. And it's still a work in progress, so take this with a grain of salt. But here in blue, we have our cross-section from our lab measured room temperature quartz versus the data we used for the Grant 2023 paper. And we're seeing that we're fitting this like blue edge of the feature a lot better, but overall the Grant 2023 is still a better fit. So we're still exploring these cross sections and also going with higher and higher temperature. But when it comes to the in situ temperature, and this is another degenerate kind of fold to throw into the mix to maybe think about, is that if the aerosol absorption is such a strong probe of temperature, and it changes so rapidly with increasing and decreasing temperature, and it's reversible. And we're thinking about how we actually observe exoplanets. We're also always observing some sort of temperature gradient. So for observing silicates along the temperature gradient at the limb, what we're really measuring is cold to hot silicate absorption. And our resultant absorption feature is going to be an overlap of all of those temperatures. And if the colder temperatures create this really steep absorption feature, and then as you go to hotter temperatures, you kind of get a more shallow redward shift, then it's possible that we're observing this sort of like lopsided temperature dependent overlap of multiple temperature dependent absorption cross sections. Of course, this is just something that me and Sarah have been thinking about that I wanted to show to this group in particular, and something we're hoping to explore further with both transmission and potentially brown dwarf spectra.
Excellent. Thank you very much. That's really exciting.